In this lecture, we will talk about the application of data simulation to soil incubation data. We will have three parts in this lecture. First, I will briefly introduce a general process of soil incubation experiments. Then I will mention about soil carbon models. After that, we will get into how to apply data simulation to soil incubation data. Soil incubation experiments are commonly carried out for studying soil organic carbon and nitrogen processes. Typically, fresh soil samples are collected from the field, crushed, sieved, and mixed before a certain amount of soil is placed in a container, for example, a mason jar. The container then receives different treatment of, for example, temperature and moisture. For carbon decomposition studies, carbon dioxide emission rate or respiration rate is usually measured repeatedly during the incubation period. With the measurements, data from soil incubation studies are usually plotted by either CO2 emission rates or cumulative CO2 emissions over time. On the left panel here, it's shown soil respiration rate on the y-axis. On the right panel, it's shown cumulative CO2 emissions, which is the data example for this lecture. In the data example, there are 36 sampling occasions over the 588-day incubation. After we have soil incubation data, we will need soil carbon models for data simulation. Generally, first-order kinetics are used to simulate the soil carbon cycle. The simplest soil carbon decomposition model simulates soil carbon dynamics as a single pool, as shown in panel A here. However, one-pool models usually simulate soil carbon cycling poorly due to various structures of substrates and protection mechanisms. So multiple pool models have often been used. For example, a two-pool model divides soil carbon into active and slow pools, as shown in panel B. A three-pool model divides soil carbon into active, slow, and passive pools, as shown in panel C. The two and the three-pool models simulate soil carbon cycling without transfers among pools. Another type of models simulates transfers among pools, as shown in panel D. Similar to ecosystem models you learned from previous lectures, soil carbon models can be described in a matrix form. The only difference of soil carbon models for studying incubation experiments is that they have initial soil carbon pool sizes at the very beginning of the experiment, but do not have carbon inputs. So I here equals 0. Now, let's get into the application of data simulation. Before we start, let's revisit the 7-step procedure again. Defining an objective, preparing data, choosing a model, using a cost function, applying an optimization method, estimating parameters, and generating predictions. First, defining an objective. Here, we want to estimate the intrinsic temperature sensitivities, or Q10s, of different carbon pools in soil carbon models. Second, we need to prepare data. As mentioned earlier, the data come from a published study. For the illustration here, data from the 25 degrees Celsius and the 35 degrees Celsius are used. Means and standard deviations of measurements from the incubation experiments are needed for data simulation. The data are organized as shown here in the table. You can find the complete dataset in the textbook. Then we need to choose a model. In practice, the length of the incubation experiment is an important aspect to consider when choosing which model to use. If the length of experiment is relatively short, for example, days to months, the one-pool or two-pool models may be appropriate. If the incubation lasts longer, for example, years, the three-pool model may be better to feed the data. Here, our purpose is to illustrate how to use data assimilation to analyze soil incubation data, and the example experiment lasts for 588 days. So the three-pool model is chosen. The three-pool model has a total of 8 to be determined parameters, including the initial fractions of active and slow pools, F1 and F2, turnover rates of organic carbon in three pools at 25 degrees Celsius, K1, K2, and K3, and their corresponding temperature sensitivity parameters, Q1, Q2, and Q3. The initial fraction of the passive pool, F3, doesn't need to be estimated, as it can be directly calculated as 1 minus F1 minus F2. The turnover rates of carbon pools at 35 degrees Celsius can be calculated as Ki times Qi. To conduct data assimilation, the prior probability density functions of the parameters are needed, which represents the prior knowledge ahead of data assimilation. When there is not much prior knowledge about the parameter distributions, the prior probability density function can be specified as uniform distributions over parameter ranges, for example, based on available literature. After having both data and model, we need to calculate the mismatch between model simulations and observations. We will adopt the cost function, the sum square of model data difference divided by doubled variance. This figure shows a snapshot of the cost function values from iteration 101 to 200 when running data assimilation. The cost function is used in the optimization step to determine whether to accept or reject the proposed parameter sets. When conducting optimization, the value of the cost function in iteration m is compared with that in iteration m minus 1. There are basically two cases when comparing the values of cost function: Jm less than or equal to Jm minus 1, and Jm bigger than Jm minus 1. For example here, J112 is smaller than J111, meaning the mismatch between model results and the measurements is reduced. In other words, the model simulation is improved. In this case, the proposed parameters are accepted. However, sometimes Jm bigger than Jm minus 1. For example, J173 is bigger than J172, meaning the mismatch between model results and the measurements is increased. In other words, the model simulation is worsened. In this case, the exponential of J172 minus J173 is calculated. Here, the value is 3 times 10 to minus 20. The value is then compared with a random number between 0 and 1. If the random selected number is smaller than this value, the proposed parameters are accepted. Otherwise, the proposed parameters are rejected. Given the number to be compared is a random value between 1 and 0, the chance for accepting proposed parameters is 3 times 10 to minus 18%. Let's take a look at another example. J159 is slightly bigger than J158. So we calculate the exponential of J158 minus J159, which is 0.01, suggesting there is a chance of 1% to accept the proposed parameters. Recall that the purpose of data assimilation is to derive global optimizations for parameters, allowing a chance to accept proposed parameters even with the increased mismatch between simulations and observations can avoid the parameter estimations trapped in local optimizations. But the chance to accept proposed parameters decreases steeply with the increase in simulation-observation mismatch. On the right panel here, we can see that when Gm is smaller than Gm minus 1, the acceptance rate is 100%. But when Gm is bigger than Gm minus 1, there is a chance to accept the proposed parameters, but the acceptance rate decreases steeply. Now, we have all the accepted parameters after finishing the MC-MC iterations. Excluding results in the burn-in period, we have posterior distributions for the selected parameters. In the figure, the distributions of parameters related to the active and the slow pools have significant single peaks, which means these parameters are well constrained. The distributions of parameters related to the passive pool, by contrast, are not as good, suggesting the data may not have enough information to constrain them. From the posterior distribution, we can derive the maximum likelihood estimates of parameters. MLEs represent the parameter value at which the distribution peaks. In the example, the Q10 distributions peak at 1.22 and 1.76 for the active and slow pools. We can use these values to represent the intrinsic temperature sensitivities at 25 degrees Celsius of the corresponding pools. The Q10 distribution of the passive pool is not well constrained, and we can use the mean value 2.67 as a reasonable guess of its intrinsic temperature sensitivity at 25 degrees Celsius. Predictions of soil carbon decomposition can be generated with the derived parameters and the model. With the generated predictions, we can evaluate the model performance by comparing observations and simulations. In this figure, the x-axis is observations and the y-axis is model simulations. Here, if all dots are right on the one-to-one line, it means the model simulations are exactly equal to observations, which of course is very unlikely. In practice, we can use a regression line to describe the comparison of model simulations and observations. The regression lines are very close to the one-to-one line here. This indicates that the constrained model fits the data very well. With the constrained model, we can also simulate the dynamics of different carbon pools during the incubation. From this figure, we can tell that the active pool dominates the CO2 emission at the early stage and is depleted very fast. At the end of incubation, the cumulative CO2 emission from the active pool is similar between the 25° and the 35° Celsius. The contributions of the slow and passive pools to CO2 emissions gradually increased after the active pool is depleted. To summarize, in this lecture, we discussed the soil incubation experiments, soil carbon models, and the application of data assimilation. Thank you very much for your attention. I'm very happy to take any questions and suggestions. You can always shoot me an email during the training course and afterwards.